Hello and welcome to this next lecture on pattern recognition. We have been discussing last class on model selection, model assessment, mainly techniques that can use training data set itself to estimate test error. And we discussed various issues such as bias variance dilemma, how one can think of test error and so on, but in cases where training data is small, which is the majority of applications, we have been looking at various techniques so that we can use all the training data for learning a classifier and as well as for estimating final errors for model selection. Okay. The one method that we considered in detail is the cross validation, right. So, the cross validation, as we have seen, is a very popular method for doing this. Essentially, using the same training data, we learn a model as well as make an estimate of the true test error. Okay. So, the idea of cross validation is the following: we divide data into k parts 1, 2, 3, 4 k. So, first time we use parts 2, 3, 4 all the way up to k for training, and then test this classifier, find the classifier's error on part 1. Next time we use parts 1, 3, 5, 7 and so on, and then test that classifier on the left out part and so on. So, essentially we divide the data into k parts, then learn k models by each time leaving out one part from the training data, which is what is used for testing. Okay. So, using this the final cross validation error estimate, the estimate and the cross validation for test error would be the average of errors of each learnt model on data points not used in the training of that model. So, each model, in each model we are using k minus 1 parts for training, one part we are not using in training that model. So, we test each model on the part that was not used in training that model, and we take average of all this, and that is our final cross validation error estimate. So, specifically this is what the cross validation error estimate is. So, f of minus rho I, rho of I denotes the part number into which xi is put. So, f minus rho I is the model that is learnt on part rho I, that is when we left out part rho I. So, the training data item xi is tested on that particular f. Okay. As we have seen last class, this is very popular method for model selection. Essentially, what you do is when you want to do model selection, there will be some alpha, which is a parameter of the model class, right. So, for different values of the model class parameter, we calculate the cross validation error estimate and then choose the best model class based on the cross validation error estimate. As we see, in model class parameters could be essentially parameters of the learning algorithm, step sizes, the C value in SVM, or the number of hidden nodes in the neural network and so on and so forth. Okay. So, generally cross validation is very often used for model selection and is also used for final model assessment. So, this is one way of estimating the true risk of a model by using the training data itself, so to say. So, here like in cross validation, we are using all the data for training and also for testing, right. So, when data size is small, we want each data element to pay. So, these are very attractive techniques. There is another technique which you also briefly considered last class, which are called the bootstrap methods, right. Bootstrap estimates provide another general technique for doing similar kind of estimation. Like in cross validation, in Bootstrap also we learn many models, but essentially in cross validation deterministically we are separating our data into k training sets. Different training sets of course share large number of things, but also each training set has some part of its own, right, because every time we are leaving one of the k parts. But here in Bootstrap, we generate many training sets by simply random sampling with replacement from the given data. We have got data points 1 to n, So, every time we want a new training data set, what we do is we keep generating random numbers between 1 and n, whichever number comes up, we pick up that particular point. Of course, some points may be picked up twice, some points may not be picked up like this. So, essentially we generate many multiple training data sets by sampling with replacement from our one given training data set. So, if given n original data set of n points, we first generate n random numbers, each uniform distributed on 1 and n, that gives me one training data set. Once again I repeat it, I get another training data set. I can like this get as many training data sets as I want, right. So, we generate let us say capital B number of such training data sets, each will be of size n by random sampling from the given data set. So, they may have of course many things in common, but some of them may be some of the points may be unique in each data set. Essentially the variation in different training data sets is coming because of the random sampling here. Okay. Then like in the cross validation case, we learn one model on each of the training data sets, right. If there are B training data sets let us say, so we learn B models, each capital B models, each one on one of the training sets. Okay. So, now we have B of hats length, B number of hats length, each one from its training data set. Now, we have the original data set anyway. So, I can choose the final error at the average of errors of all the models on the original data set I have, right. So, basically what is the difference between cross validation and bootstrap? Unlike in cross validation, here we can have as many training sets as we want and all of them of the same size, right, because the variation comes by random sampling. In cross validation, because I am actually partitioning data, at most I can partition to n parts, the leave one out cross validation. Beyond that I can't partition it. But here, because I am random sampling, I can generate as many training data sets as I want and all of them will have size n. The flip side of course is that while I can generate thousands of them, many of them might be very similar, because I am just sampling with replacement from the same underlying data. So, maybe they might all be similar. Any case, let us first look at the error estimate. Let us say f hat b, f hat small b denote the model length using the bth bootstrap sample. B takes values 1 to capital B, right, that many bootstrap data sets are there. So, let us say f hat b denotes the one length on the bth one. Then my error estimate is very simple, I will call it E1 boot, the one because we will have another error estimate later on. So, this is a bootstrap error. So, if I take the inner term 1 by n summation I is equal to 1 to n L of f hat b x i y I, this is the average error on the original data set of the bth model that is length. Now, I take average of all the B models, the average error of all the B models, that is my final error estimate. Okay. Seems quite reasonable, except that there is only one problem. See, essentially this is like for each model f b, I am using the entire original data set as a test set, because this is like a test like error on the entire original data set, and then I am taking average of these errors. So, here we are using the original data set as a test data set, so to say, but for learning f hat b, we used some of the same data points, right. So, obviously, because f hat b has used some of the x I y I, we have used some of the x I y I for learning f hat b, this error estimate is likely to be poor. Matter of fact, it can be very poor, right. Let us take an example. Let us take an extreme case where the feature vector and the class label are independent. That means, I get some feature vector, but the class label for each feature vector, each pattern is independent. So, with the 0.5 probability is class 1, 0.5 probability the other class. Okay. Now, then if I am using a 0 1 loss function, my true error rate is just 0.5, right, because class label is not correlated at all with the feature vector. So, because class label is random, the best I can do is 0.5. Okay. Now, let us say I am using a nearest neighbor classifier, one nearest neighbor classifier. So, my classifier would be I take my training data set, stored it as my prototype. Every time I get a new pattern, I look for the nearest neighbor in my training data set for that. and give the same class, right. The like k nearest is the one nearest neighbor, the nearest neighbor classifier. Now, what happens? Because you are using the same x1, x2, xn for testing, on any xi, the classification with f hat b would be correct if xi is in the bth bootstrap sample. If xi is in the bth bootstrap sample, right, then xi will be one of the prototypes of f hat b. Now, when you are testing using xi, I ask what is the closest pattern to xi, it will be xi itself, and I will give the correct class label. So, on any xi, the classification by f hat b would be correct if the particular xi happen to be in the bth bootstrap data set. If it is not there, then obviously there will be something else that is nearest, but it really does not matter because class labels are random. I can get correct class label with probability only 0.5, right. So, for my one nearest neighbor, the bootstrap error, expected bootstrap error would be 0.5 times the probability that a random xi will not be in the random bootstrap, as an arbitrary bth bootstrap sample, right. We can calculate this probability. Let us say I want to calculate the probability for some I and some b, probability xi belongs to bootstrap sample b. How did I generate the bootstrap sample? I keep the sampling uniformly over the 1 to n samples, right. So, the only way is, first let us ask when will xi not belong in the bootstrap sample. So, when I did one sampling from the data, a specific xi not coming is 1 minus 1 by n. I did n such samples. So, the specific xi not coming is 1 minus 1 by n to the power n. So, xi coming is 1 minus 1 minus 1 by 1 by n to the power n. It is clear? Because each sample can come with probability 1 by n, right. Whenever I sample once, a specific xi not coming is 1 minus 1 by n. So, when I do n times sample, the specific xi not coming on all the n times is like getting n heads in n tosses of a coin. So, 1 minus 1 by n to the power n, and if I want the probability xi is in it, it is 1 minus 1 minus 1 by n to the power n, right. If n is large, we know 1 minus 1 by n to the power n goes to e, so goes to e to the power minus 1. So, this is roughly 1 minus e to the power minus 1, which is about 0.63. Okay. So, this does not depend on I or b. For any I and b, probability xi belong to bootstrap b is about 0.63 for log. Okay. This approximation of this to e power minus 1 is fairly good. So, which means the expected value of our E1 boot is, because this is 632, xi not being in the bootstrap sample is 0.378 or 0.368, and into 0.5 will give me about 0.184, right. So, we have seen that if it is not, if it is in, I anyway do not make error. If it is not in, I will make error only with probability 0.5. It is not being in the bootstrap sample is about 0.36. So, that into 0.5 is about 0.18. This is the expected value of E boot. This is my estimate. The expectation of the estimate is 0.184, whereas the true value of the error rate is 0.5. So, the expectation of E boot is very far from the true value. So, we have large amount of bias. So, E boot, E1 boot is a high bias, highly biased estimator of the true risk of the classifier, and is biased down obviously. So, it is underestimating the error rate. We can actually reduce this bias by using what we did in cross validation, that is, test each model only on those data samples which are not used in learning it. Now, of course, because the data samples are obtained randomly, just notationally writing this is a little complicated, but let us write it anyway. So, now we will define another error estimate, this time I call it E boot, that one is not there. So, for each I can test I on all f hat b in which it is not used. So, let us define C minus I, the set C minus I to be the indices b bootstrap sample indices, bootstrap data set indices, such that xi is not in that bootstrap data set. So, C minus I gives me the set of all bootstrap, the indices of all bootstrap data sets in which xi is not there. So, for each of these little b in C minus I can take the error on xi. So, because I want average, I divided by the number of elements in C minus I, right, and this is the contribution to the final error estimate of xi, and I sum it to or I equal 1 to n and divide by 1 by n. I hope it is clear. Essentially, each xi can be used to test f hat b for all b such that that xi is not used in training f hat b. So, the set of b on which xi is not used in training f hat b is C minus I. So, I sum this over b belonging to C minus I and divide by the number of elements in C minus I. Okay. That gives me the amount of error estimate contribution from xi. I get it from all the training samples. Of course, there is a possibility that for some particular xi, C minus I is null. If C minus I is null, I just do not take that xi, because I can't divide by 0. So, I will just omit that particular I. If I omit that particular I make it 1 by n minus 1, right. But if b is large, this is unlikely to happen. If b is large, that I have been doing many large sampling, there is a particular xi which never comes into any of the samples, is a very rare event. So, if capital B is sufficiently large, this case may not happen. In any case, this kind of a bootstrap estimate is sometimes called leave one out bootstrap estimate of error. Okay. So, bootstrap is also another good way to estimate test error, right. Basically, to contrast with cross validation, in cross validation we divide data into at most n parts, and hence there can be only n different models you can learn. On the other hand, in bootstrap we can choose b as high as we want, right, and still have proper set training sets. Now, because we average it over so many models, we are likely to get low variance in the error estimate. Okay. But on the other hand, the training sets that we can get like this by sampling with replacement are all quite similar. Right. See, for example, in cross validation we said we would like to do 5 or 10-fold cross validation, so that we can keep the variation in the training data set. If we do leave one out, the variation in different training data sets is very small. So, the model's length may all be similar. So, the estimate may not be very good. The same thing may happen here. Okay. Another way of looking at it is that from what we calculated, any xi being in any particular bootstrap sample is about 0.63, which roughly means that each bootstrap sample would have about 0.63 n distinct samples. Right. So, this is like a 3-fold or 2-fold cross validation, right. So, it contains about 60% of the 63% of the total number of samples. So, if I did 3-fold cross validation, each training data will contain 66% of the original data. 2-fold cross validation contain 50% of. So, essentially for the biases and so on, it will behave like this. Okay. But of course, because I am generating many beats, it will not be just like 3-fold cross validation. The averaging because of beats can give me a better estimate than a 3-fold cross validation. Okay. So, there are both pluses and minuses for bootstrap in relation to cross validation. This is also a very general statistical technique, can be used for estimating many quantities from data. This has also been used, as I said, as a variance reduction technique in your estimate. Okay. Okay. Next we consider what is called bagging of the estimates. Okay. Let us take Bootstrap. Of course, what I am saying about Bootstrap is also true of cross validation, but in Bootstrap we are generating many different training data sets by sampling from the original data. So, we have one set of n examples xi, yi. then we are generating many different training data sets by sampling with replacement from them. We are doing this essentially so that we learn B number of models f hat B, okay, because we generated B data sets. What is the purpose of generating all these models? We use all these models together to get a good estimate of the expected error. This could be for model selection. So, we want to know how good a model class parameter alpha is. So, for that class alpha, I learn so many models and then I know how good it is. Ultimately, I can find what is the best alpha to use, or I may use it for final model assessment. And same thing is true of class validation also. There, unlike here B being arbitrary, that may not be arbitrary, but tenfold class validation or whatever, we are learning many different models. Now, I got an error estimate, I finished all this. Let us say I did model selection, I got the particular alpha. For that alpha, I have many f hat B alphas, or I have anyway learned many f hat B's, and finally did my model assessment. But along the way, I have learned so many models. So, which particular model should I use as the final model? Should I throw up all this away and once again relearn? After all, there is no difference from learning with one more training data set. Say for example, in task validation, any one of the models can be used at the final model. Which model should I use? A good idea is, why can't we use all these models to improve the prediction? Right? Anyway, I have learned so many models from so many different training data sets. Why should I throw some of them away? When you give me new patterns from now on, I can use all the models and maybe somehow combine them to get a better prediction. Right? Now, this is the basic idea of bagging. Bagging is one way of improving the prediction of the final model. So, instead of using any one of them, if I use all of them, then I may get a better prediction. So, what is the simplest way of using all of them? Averaging. Okay? That is what simplest bagging estimate is. So, actually bagging is a kind of word derived from Bootstrap aggregation. That is, I aggregate all the Bootstrap models, and also is a nice term because I have a bag of classifiers, bag of models. Okay. So, bagging stands for Bootstrap aggregation. The idea of bagging is to average over the predictions of all the models. So, given all the Bootstrap models that we learn, small b is equal to 1 to capital B, the bagging model prediction at a new point x is given as f hat bag of x is the average of all the f hat B of x. Right? Because the actual theoretical definition of the bagging estimate is not like this. It is the expectation of f hat B x, where B is a random Bootstrap model that you obtain. So, which means this expression actually is itself an estimate of the bagging estimate, right? An estimate derived as a sample mean, because I do not know how to find the distribution of how different Bootstrap samples behave, right. So, for a random Bootstrap sample, what the model error is what bagging estimate is. So, to get that, I just average over many specific actual Bootstrap samples that I derived, right. So, to be technically correct, I have to say that this is a sample mean estimate of size B of the true bagging estimate, but that is anyway, that is just a minor mathematical precision problem. But essentially, a bagging estimate is to average out all the models you learned. Okay. So, often bagging can improve performance of the final model. Okay. Instead of using any one of them, if you use all of them and average out, of course, I have to ask what averaging means in a classifier context. In a regression context, I can immediately see what averaging means. In a classifier context, what should I do? Then maybe, essentially, if it is a 2 class problem, I can take f hat B to be plus 1 minus 1. Then I can take the sign of this average, but if I am taking sign, of course, that 1 by B makes no difference. So, there is various ways of doing this, but essentially roughly at this point of time simply say average. For regression models, average is what all of us think as average, you just true average, because you are anyway predicting a real number. For classification, currently average simply means majority, right. You look at all the predictions and take the class label that is output by the majority of your models. Okay. That is what averaging would mean for classification. Now, essentially the bagging estimate that we introduced is one way of using multiple classifiers instead of one. So far, we have just been saying, given one training data set, how do I learn one classifier? Now, bagging uses all models learned from different bootstrap samples to predict the new data. So, I can think of bagging is an example of a method that combines multiple classifiers to improve accuracy. Right? Now, intuitively, instead of using one classifier, if you use many classifiers, one should improve accuracy. Right? If this is like I ask many experts for something. If I am preparing for an exam, I do not know a question, I do not understand something, I can go to one of my classmates and ask him to explain it to me. Well, I do not know which one to choose, all of them might be just as bad as I am. So, instead of asking one, if I ask 10 of them, maybe together they will give me all the things that are there to learn. Right? This is like going to multiple experts. In many situations, this is a nice strategy. A simple example which all of you would have seen is the audience poll in Kaun Banega Crorepati. Right? In Kaun Banega Crorepati, there are when the contestant does not know answer to the question, one of the lifelines is the audience poll, whereby you ask all the people in the audience. Of course, nobody in the audience is any great expert to know the answer. Each of them may have only 55%, 60% chance of knowing the answer, which is same as the contestant's chance. But if you ask enough of them and go by the majority, very often it works. Right? So, even if each individual classifier is not very good, right, may have only 55-60% chance of being correct. If I have enough of them, right, like in the Kaun Banega Crorepati audience poll, it looks like I might be able to improve my accuracy much better than asking any one of them. In the audience poll, suppose instead of polling the audience, the contestant is allowed to choose a particular person in the audience and ask. It wouldn't work. Any one of them is not particularly great. It's very difficult to choose somebody who is likely to be correct on this one question. But if you have sufficiently many randomly chosen people there, then averaging often gives you the answer right. Now, this is the basic idea of combining classifiers. Okay. So, that is what we are going to consider next in this course. So, that is more or less the last topic of the course. So, how does one combine classifiers? One basic technique for doing this is what is called boosting. Boosting is a procedure that combines many what can be called weak classifiers to produce a better one. Weak in the sense, no classifier individually is a great expert at classification, right. It may not get very high accuracy. Technically weak means that their expected error is just less than 0.5. I mean, may be only 0.5 minus epsilon, right. They may not be very great classifiers. But if you have sufficiently many of them, the idea is we can combine them to get a classifier with high accuracy. So, this is a method of combining classifiers and is sometimes called an ensemble method, an ensemble classifier method, because it uses an ensemble of classifiers. So, classifier combinations, classifier combiner, ensemble classifier, all these essentially mean the same thing. In all these cases, the method uses multiple classifiers, and given any pattern, the class label that it outputs is some combination of the class labels given by all the classifiers. Okay. Boosting is one such method, one of the most important methods in classifier combination. So, in this sense, boosting is like bagging. Of course, bagging is also a classifier combination. It simply says take n models and take majority or average depending on you doing classification or regression. So, in that sense, boosting is similar to bagging. But there are some very important differences between the basic approach of boosting and what we see in bagging. In bagging, we are just taking B random classifiers, B classifiers trained on random data sets and taking their average. But boosting is not quite that. In bagging, the different classifiers are trained on data sets which are just randomly sampled from given data. So, any variation in different training data sets essentially comes out of this random sampling. There is nothing else. There is no purposive variation in different training data set. We are not purposely looking for variation in the training data set. Just this random variation which comes because of random sampling is the only variation present in different training data sets and hence in different classifiers. We have not actually taken any care to see the different classifiers in the ensemble complement each other. See, for example, if you are going for a quiz competition, you send a team. This is like a classifier ensemble. Instead of having one person, a team. When you choose a team, you do not choose 3 people who all of whom perform very well on some written test that the school conducted. That may not be the best thing, because say all 3 of them have only one strength, say sports. That won't work. So, even if somebody got a little less marks in that entrance test conducted, if he has complementary skills, let us say he can cover music which nobody else knows, he is a very valuable member for the team. Somehow, if you want a team of classifiers, an ensemble of classifiers to do better than individual ones, somehow each one, the different classifiers in the set have to complement each other. Each one has to cover for the other people's deficiencies. Right? Only then the team would be more than the sum of the individual parts. Okay? So, that is what one would normally like. Right? So, for example, in my Kaunbanaga Karupati example, if I put in the audience people who are all clones of the same person, it is of no use. Right? In practice, it works because they come from different walks of life, they are all randomly chosen from different socio-economic backgrounds, different educational backgrounds. So, there is a lot of variability in the individual classifiers. Somehow, we have to have that variability, so that the team will combine well. So, basically in boosting, we like to introduce such variation in the classifier ensembles. It is just generating random data sets and training classifiers. Of course, we still generate random data sets, but we want to purposefully introduce some variation in the classifier ensembles. Now, how can I introduce variation? Essentially, the only way I can, the only difference in different classifiers is the training data sets on which they are trained. So, I have to somehow create different training data sets which are different, which are the right variation. Okay. Simple intuitive example to convey this idea of boosting. Okay. Let us say I am wanting to create a classifier ensemble with 3 component classifiers for a 2 class problem. Okay. So, let us say we have a training data set, the endpoints, let us call that script D. So, I have to now generate 3 separate training data sets to train my 3 component classifiers in the ensemble. What do I do? First one is no problem, I have to just generate some training data set. Let us say I randomly select some n1 points, n1 less than n from D. I put them in a set called D1, and then I train my first component classifier on D1. This is fine. So, I just, of course, this is not completely fine. I have to know how large or small n1 should be compared to n. That is very much problem specific, and this is only anyway an example to give you some idea of boosting, trying to do some variation. So, let us stick to that. Let us say I chose some n1 data points. So, we learn our first component classifiers, they call it H1, use the training data set D1. Now, our idea is for learning the second component classifier H2, I do not want some other random n2 points from n1. Then I cannot really ensure that H2 has right variation compared to H1. So, I want to ask what is a good data set to train H2. One way of saying this is the data set, say call it D2, on which I want to train H2, on which I want to learn H2, should be such that given the classifier H1, the data set is most informative for classification. Most informative means the data set is completely surprising for the classifier H1. Okay? If the classifier H1 can easily explain away the data set, then the training on the classifier on that set makes no sense, because H1 is doing well on this. So, it is not that on the data set H1 should do very well or very poorly, but the data set should be somehow very surprising to H1. What do we mean by this surprising to H1? The performance of H1 on D2 should be no better than pure guessing. If suppose H2 gets 0 correct on it, that means I know all of them are very hard problems. That may be simply compliments of the original things. On the other hand, H1 does very well also is useless. But essentially is most informative when in D2 the performance of H1 on D2 is essentially like pure guessing, meaning roughly about half the points in D2 are correctly classified by H1 and half the points are incorrectly classified by H1. So, H1 does not even know he is making errors. Right? So, some it gets right, some it gets wrong, but it is completely surprising to it because it looks like the particular characteristic of data H1 learned does not apply to D2, because on that characteristic half the points are classified correctly, half the points are classified incorrectly. So, in that sense D2 has the most surprise for H1. Now, can I generate this? Yeah, I can generate this. What do? I make D2 by choosing from D1 with probability half the remaining points in D1 which are correctly classified by H1, probability half points incorrectly classified. What does that mean? I first take away all the n1 points from D. Now, in the remaining points I start from the beginning. I keep looking, I first toss a coin, I first generate a round number. A round number comes less than 0.5, that means the coin falls heads. Then I am now looking for something that is incorrectly classified by H1. So, I keep going down the points in D, the points in, so to say, D minus D1 till I find a point which is incorrectly classified by H1, put that in D2. Now, once again toss a coin, suppose this time coin falls tails, that means this time my random number goes more than 0.5. Then I now looking for a point in this set, in the set D minus D1, which is incorrectly classified by, which is correctly classified by H1 and so on. So, I keep choosing points, removing points from D minus D2 like this. So, that with probability 0.5 I am choosing points which are correctly classified by H1, and with probability 0.5 I am choosing points which are incorrectly classified by H1. So, the D2 will roughly have about 50% of the points correctly classified by H1, 50% of the points incorrectly classified by H1. So, this gives sufficient variation in D2. Now, we will land a classified H2 using D2. Right. Next what? What do I do with H2? How do I? Now, I know I am using only 3. If I am using many, I can keep doing this kind of thing. But if I am, because I know I am using 3, H3 is like a tie break now. I try to get H1, H2 learn as much variation as possible, but H3 should be a tie break. So, if H3 to be a tie break, then what we can do is take the original data set and pick up all the points in which H1 and H2 differ. Then put that in D3 and learn H3 and D3. Right. So, what did we do? We made our third classifier specialize in resolving the cases where H1 and H2 differ. Right. So, because we are using only 3 classifiers, we put sufficient variation for H1 H2, so that H1 H2 cover for most of the space, and then we made the third classifier specialize in trying to classify those cases where H1 H2 differ. Okay. So, now how do I use this ensemble? Because I know how I trained them, this is how I am going to use my ensemble. If you give me a pattern X, I find H1x and H2x. If H1x equal H2x, that is what is the class I will give. On the other hand, if H1x is not equal to H2x, then whatever H3x is what I output. Of course, this is actually a majority, right. If H1 is equal to H2, H1x is equal to H2x, no matter what H3x is, that is the majority. If H1x is not equal to H2x, once again whatever H3, because the 2 class classifier, whatever H3 says is the majority. But it is not just a simple averaging. The idea is that because of the way I am trying to use this classifier combination, I have trained them differently. That is basic idea. The basic idea is I put some variability in the training data, so that this kind of averaging pays well. This kind of averaging gives me a better classifier. Okay. This is the basic idea of boosting, that instead of just randomly generating new training data sets and just averaging, try and generate more informative training data sets for successive classifiers. Okay. So, that is the basic intent of boosting. Okay. Boosting can be seen to be one of the major ideas to come into pattern recognition in the last 15 years. As a matter of fact, over the last 20 years, the two fundamental advances that this field has seen. One are the support vector machines and kernel based methods, right. Other is this idea of boosting, classifier combinations, right. These two are really fundamental advances to in the theory and practice of pattern recognition. Okay. So, in the sense, boosting is a very important technique. For a general purpose boosting algorithm, we need some automatic way of generating training sets, right. This what I call more informative training sets. I have to have some way of generating. See, in that method I do not know how much n1 to choose. If I have to choose in the remaining n minus out of the remaining n minus n1 samples only for D2, I may have sufficient, may not have sufficient, and now after that I may not have any more samples left for training more. So, that specialized thing is only an example to give you an idea of what I mean by choosing training data sets, so that different classifiers are trained on nicely informative data sets. But we need some automatic way of generating training sets from the given original data, right. And we also need some general method of combining outputs of different classifiers, right. What averaging, what kind of majority is right. Right. So, any boosting algorithm has to do these two. Okay. What we are going to do is to look at one such algorithm, which is called AdaBoost. It is a very influential one of the most important and most popular boosting algorithms. Of course, AdaBoost can be used for classification, regression. There are different variations of AdaBoost. This is the first level course, so to say, and given that we are almost at the end of the course, we will consider only one simple case of AdaBoost, that is for two class classification, but it gives you the full idea of how that kind of general purpose boosting is done. Okay. The basic idea of AdaBoost is the following. In AdaBoost, so we have the initial data set x1, x2, xn. So, for each xi, we assign a weight, maybe a weight called wi. So, we assign non-negative weights to the points in the data set, and the weights are normalized, so they sum to 1. So, you can think of the weight as a probability. Okay. Then, the idea is that I iteratively, the algorithm in each iteration learns a new classifier, just like the boosting algorithm we saw, it learns 3. So, 3 you can learn as many as you want. At each iteration, you have to learn new classifier. To learn new classifier, I have to have a training data set. So, in each iteration, I generate a training set by sampling from the data using these weights. I use these weights as a probability distribution and generate IID samples out of the distribution. That means, a particular xi is chosen with a probability proportional to the weight, and I keep making many IID realizations of this to generate a training data set. So, what I mean is, a data point xi by I would be chosen with probability wi, where wi is the current weight for that point. Okay. Of course, as we said, we always keep wi normalized, so that they sum to 1. So, we generate training data set by I first choose get a random number distributed as w1, w2, whichever one it falls in, I pick that xi. Once again, do repeated independent sampling like this. So, we generate a training data set by repeated independent sampling using the weights. Then, after learning the current classifier, what we do is we change the weights. We essentially increase the weights for the points that are misclassified by the current classifier. Whatever points out of my data are misclassified by the current classifier, I increase the weights of those points, right. And then, using the modified weights, we generate a fresh training data set, and once again learn a new classifier and so on. And the final classifier, we essentially use a weighted majority voting, where the weights are in some sense proportional to the accuracy achieved by each classifier. So, a classifier with slightly higher accuracy would get higher weightage for their, but of course, it is not directly accuracy. We have to know, we have to use the right scale to give the weights. Okay. But anyway, AdaBoost uses some such thing. So, it uses a weighted majority for all the classifiers. Okay. So, this is the overall intuitive idea. So, let us go for the algorithm. So, let us review our notation. We are considering a two class case. The data is x1, y1, xn, yn. n data points, and we take 2 class. So, we take yi to be plus 1 minus 1. Okay. We wi of k denotes the weight for the ith data point, that is xi yi, at kth iteration, right. We are learning classifiers iteratively. So, at the kth iteration, the weight assigned to the ith data point is denoted by wi of k. We denote successive classifiers h subscript k. So, hk denote the classifier length at the kth iteration, and is a classifier. So, hk of x for any x will be either minus 1 or plus 1. Okay. We assume that the error rate of each classifier on its training data set is less than 0.5. Okay. Otherwise, of course, the method will not work, but I'll point it out in the exact algorithm where it comes. Okay. Essentially, the idea is that I do not need my individual classifiers to be too big, right. I can choose them to be simple ones. So, if for example, if I choose those classifiers to be of low complexity classifiers, right, small size neural networks, or a simple decision tree, or or a simple linear classifier, then because the model complexity is small, even with small data item, within that class I can learn a fairly good classifier. That classifier may not have great accuracy, but basically by boosting, even though those individual classifiers may not have very great accuracy, their error rate is only maybe 0.5 minus epsilon, by having enough of them I can do very well. And because I do not want individual classifiers to be very highly accurate, I do not have to go for very high model complexity. This is how the basic idea of boosting pays. Okay. Okay. So, let us consider the algorithm. So, to start with, I put weights as 1 by n. In the beginning, there is nothing to choose one data point or other. So, all weights are equal, and as you can see, the beginning the weights sum to 1. Then it's an iterative procedure. Let us say capital M is the number of iterations, that is capital M is the total number of classifiers I am going to learn, right. So, little m is my iteration count. What do? I first generate a training data set by sampling with these weights, right, using my current iteration count, my current weights wi of m, I generate a training set. Then I learn a classifier hm using this training. The classifier can be anything, as a matter of fact, in different iterations I am even allowed to learn different classifiers, even though in a program sense I have to decide on which iteration and which classifier I learn. But as far as the algorithm is concerned, different classifiers need not have to be the same type either. Let us say on all even numbered iterations I learn using linear least squares, on all odd numbered iterations I may learn an oblique decision tree, or I learn a neural network. So, but essentially I learn some classifier hm using this training data set. Then I calculate xi m, which is a kind of weighted error of this classifier. So, xi yi is the data set. Okay. So, if yi is not equal to hm xi, the classifier hm has made an error on xi yi. That error is weighted by the weight wim. Mind you, xi yi may or may not be in the actual training data set using which I learnt hm, right, but I do not care about that. Just after learning hm, for each I, if yi is not equal to hm xi, that if I made an error, then I add wim for that error. So, the cost of error is not equal, errors are not simply counted, they are weighted by the current weights. That is the error rate, right. The idea is, if a particular I has high weight, it is likely to be represented more than once in the training data set of hm, and hm would have certainly taken care of that, right. So, that is the whole idea. So, we assume that this xi m is less than 0.5. In practice, what it means is, after I generate a data set and learn a classifier, if my xi m does not happen to be less than 0.5, I just throw it away, run the iteration again. I once again get another data set by randomly sampling with the current weights only, and learn again. Very often, many of these classifiers are reasonably good. So, even at hard data sets, they can give better than 50% accuracy. So, we mostly always get xi m less than 0.5. Then we calculate alpha m, which is natural logarithm of 1 minus xi m by xi m. Because we assume xi m to be less than 0.5, 1 minus xi m is greater than xi m, which means alpha m is always positive. Okay. So, we calculate this weighted error, this is what we call error rate of mth classifier, and then we calculate this alpha m. Now that we have learned the classifier, the next step is I have to now find the next set of weights. This is my weight update rule. So first, given Wim, I calculate Wi prime m plus 1. The whole idea Wi prime m plus 1 is not normalized. So to get Wi m plus 1, I normalize Wi prime. Okay. So first Wi prime m plus 1 is calculated by Wim into exponential alpha m into I of yi not equal to hmxi. By the way, I didn't indicate this, but this I is an indicator function. I of a is 1 if the event a is true, is 0 if false. So I of yi not equal to hmxi is 1 if y is not equal to hmxi, 0 if y is equal to hmxi. Okay. So that is how Wi prime m plus 1 is calculated, and then I normalize Wi primes to get the weights at the next iteration. So this is what I keep doing for m is equal to 1 to m, right, a, b, c, d, e. Once I finish it, my final classifier, mind that each of hm's are plus 1 minus 1, right. If sum is not there, as you already seen, if alpha m is not there, this is simply a majority vote. So I am weighing the votes by alpha m, and alpha m is some measure of the accuracy. Okay. So, but anyway, we will come back to this later. So, this is the final classifier. Okay. So, this is the AdaBoost algorithm. Okay. So, I generate training set by sampling with the weights, learn a classifier, then calculate the error of the classifier, which is equal to weights of all the data that are misclassified with this classifier. Then I calculate alpha m, which is ln 1 minus xi m by xi m, we are assuming xi m less than 0.5. So, alpha m is always positive. Then I update weights like this, that is it. I do it iteratively for m and then use all the m classifiers. Okay. Let us look at some of the characteristics of this algorithm. M is a parameter first. So, I can choose any m, because I keep sampling with weights, I can continue this process for arbitrary number of iterations. So, there is no limit except computational resources and things like that on how many classifiers I can use in my combination. So, in that sense, it satisfies my first requirement for a general purpose boosting algorithm. It should be able to keep automatically generating as many training data sets as I want. Now, for a particular high, if hmxi is equal to yi, right, then this indicator is false, then Wi prime m plus 1 is equal to Wi prime m, because the exponential 0 is 1. On the other hand, if this yi is not equal to hmxi, then this is 1, this exponential alpha m is positive. So, exponential alpha m is greater than 1. So, Wi prime m plus 1 will be greater than Wim if y is not equal to hmxi, meaning the ith sample is misclassified. So, if ith sample is correctly classified, hmxi is equal to yi, then Wi prime m plus 1 is equal to Wim. On the other hand, if hmxi is not equal to yi, then Wi prime m plus 1 is greater than Wim, and because the normalization, which does not change this relative values, if ith sample is misclassified, then Wim plus 1 is greater than Wim. So, as I told you in the beginning intuitively, our equations ensure that if the current classifier misclassifies a pattern, then the weight of that pattern for the next iteration is increased. Okay. Of course, this by itself is not enough. If we keep arbitrarily increasing weights of misclassified patterns, then the subsequent training sets can be predominantly only misclassified pattern. As we said, that is not enough, that is not the right variation, right. To have right variability, we want the pattern sets to contain about half the samples misclassified with the current classifier, half the samples correctly classified with the current classifier. Right. So, I cannot just arbitrarily increase weights, but this algorithm has a very nice weight increase formula, which ensures at every iteration that after I update the weights, if I add up weights at the next iteration of all I which are misclassified by hm, that will be same as the weights of all I which are correctly classified by hm, and so both of them has to be equal to half. So, half the weight is for patterns correctly classified by hm, half the weight at the m plus first iteration is for patterns incorrectly classified by h. So, when I am sampling my data, my training data, sampling from my training data at the m plus first iteration, likely that half the patterns will be ones which are correctly classified by HM, half the patterns are incorrectly classified by HM. So, let us just prove this. Okay. This is a very surprising result, but it is worth proving, and then we will look at more details of this thing again. For the proof, let us remember weight update formula once again I wrote here. Xi m is given by this, alpha m is given by this, and this is my weight update formula. Okay. We will come back to this again and again. So, by definition, see Xi m is this. So, I can actually convert this onto index here. So, you sum over only those I for which y is not equal to HM xi. So, I can write Xi m is sum over I, so that HM xi not equal to y wi m. Now, since WIM or sum over all I of WIM is always 1, if instead of summing over I so that HM xi not equal to y, if I sum over HM xi equal to y, I get 1 minus Xi m. Okay. Also, alpha m is ln of 1 minus Xi m by Xi m. So, exponential alpha m is 1 minus Xi m by Xi m. So, what does this mean? If HM xi not equal to yi, then Wi prime m plus 1 is Wi m into 1 minus Xi m by Xi m. If HM xi equal to y, then Wi prime m plus 1 is Wi m. Now, we can use this as follows. Suppose I sum all the Wi primes, then I can sum over all I such that HM xi is not equal to y, I such that HM xi equal to y. So, this sum or all I of Wi prime are split into two sums, those I such that HM xi not equal to y and the remaining I. Now, for those I such that HM xi not equal to y, I know what the value of Wi prime m plus 1 is, Wim, not no prime here, Wim into 1 minus Xi m by Xi m, and for the ones where Hm is correctly classified, Wi prime is simply Wim. Now, this is not dependent on I, and sum of Wim such that HM xi not equal to y, we just now calculated, that is Xi m, right. Xi m by definition is sum of Wim such that HM is not equal to I, and this we already seen is equal to 1 minus Xi m, right. So, which means the sum over I of Wi prime m plus 1 is always 2 into 1 minus Xi m. Okay. Given this, let us say I want sum of Wi m plus 1 summed over all I which are misclassified by Hm, right. That is, for the ones misclassified we just now seen Wi prime m plus 1 is Wim into 1 minus Xi m by Xi m. So, Wim plus 1 is Wi prime m plus 1 by the normalizing constant. The normalizing constant we have just now seen is 2 into 1 minus Xi m. So, this 1 minus Xi m will cancel with this 1 minus Xi m. This gives me 1 by 2 Xi m into sum over I such that HM xi not equal to yi of Wim, right. This we already know Xi m, this is half. So, we have shown that sum over I such that xi y is misclassified by Hm, the weights at the next iteration is half. So, the weight update is such that at the next iteration half the weight of the pattern misclassified by the current classifier and the remaining half is for patterns correctly classified by the current classifier, right. So, this is a very interesting weight update rule. In the next class, we will look at a few more interesting facts about this algorithm, which is what makes it a very great boosting algorithm, and then show that we can actually look at it as a very interesting disk minimization under a special kind of loss function. Okay. So, next class we will look at AdaBoost algorithm again and give you an overview of a view of AdaBoost algorithm as a disk minimizer. Okay. Thank you.